Thanks. It's really great to be here. I'm super excited about audio, and please interrupt me if something doesn't make sense or if you have a question, because I mean it's a small group, and why not? So the reason I made this presentation is because I'm a very visual thinker, but I feel like there's a lot of visual on the web. I feel satiated in that sense. So really what I want to explore is audio on the internet, because I mean I'm a music lover. I think Scott, myself, you all, we're all people who love music, and we should pursue that love and our love of JavaScript on the web. So HTML5 introduced a bunch of neato, cool new tags, and one of them is the audio tag, seen here, playing
Code Monkey have boring meeting with boring.
So that's the audio tag in its default form on Chrome, and I'm sure Scott will dig in very soon on all the compatibility issues and all of the cool stuff you can do with that. So basically, you can control it using JavaScript. You can get some metadata, and you can play sounds from the internet. That's pretty cool. But what I'd really like to talk about is how to play with music on the internet and do some dynamically generated audio. But first, I'd like to step through a little brief computer history, because I think it's really cool to look at how we've progressed over time. Starting with CIRAC, which is the world's first computer that ever played music. So I have a video of that here. So this is basically the state of the art of the 50s. Pretty cool. So yeah, step forward about a decade, and we have computers simulating human speech. I'm always astounded by academia and how fast they get computers to do cool new things. I feel like I'd be a lot slower just hacking around.
Daisy, Daisy, give me your answer too.
So that's pretty cool, right? In the 60s, we had a computer that was able to sing. And this guy over here, Arthur C. Clarke, was so impressed by that that he actually contacted the researchers and used that sound in the movie 2001: A Space Odyssey. So in 1982, we had MIDI, and most of you have heard MIDI annoyingly auto-playing on a 90s era website. And Chick Corea is very famous for using MIDI and synths of that era. So in 2011, well, what do we have in 2011? We have HAL 9000? I hope not. What we do have is iPads, and those provide a really cool interface for people to interact with music. And we also have JavaScript music. It only took 20 years, right? Or maybe 15 years. But now, without a plugin, without Flash, without Java, we can generate audio on the web. And it sounds basic. But, oh, whoops. Pressed the wrong button there. It sounds really basic, but the fact that we can do it and the fact that we can experiment with it is really cool and really exciting. So what I'd like to do is step everyone through just a quick guide on how to generate audio dynamically and how to generate wave data dynamically. And we're going to use that to play around with a couple basic synths and talk about how that all fits together. But first, I'd like to tell you a little bit about sound theory. So everyone's familiar with sound waves, right? You may have gotten this in college physics before, but I'd like to quickly jump through it. So when we talk about waves, it's kind of an abstract concept to many people. But what we really perceive are pressure waves in the air that propagate through the air from my mouth or through the speakers to your ears. And when a computer is when we're talking about audio signals in the context of a computer, we're talking about analog electrical signals. This is basically the variation of voltage over time that drives speakers and makes sound. When we're doing that digitally, basically what we're doing is we're slicing that wave up into lots of little pieces, and we're sampling the specific amplitude of that wave at a specific time. So we have all these little discrete points. We turn that into sample data, and then we put that on the internet with this cool Metallica MP3 on Napster. And then to play it, we convert it back to an analog waveform. We pipe that over to our speakers, and then it turns back into pressure waves, and you can hear it. So, oh no, that's not good. I think I have some fonts missing. But a couple basic concepts. Frequency is 1 over frequency is basically it's the pitch we hear, and it's 1 over the wavelength of the wave that you're hearing in the case of in basically a basic sine wave. And amplitude is how high and how low the wave varies, which is our perception of volume. And finally, we have this concept with computers of sampling rate, which is how far apart those individual samples you take are. And this basically, when you're sampling, you're not getting a perfect copy of the analog wave. The analog wave is to our senses, infinitely detailed. The sampling rate is how often you're taking a single snapshot of that and turning it into a wave. So this is stuff most of you are probably quite familiar to. So let's get down to making waves. But actually, what we're going to do is make waves, wave files. You're probably familiar with these in the early Windows era. They were basically the best way and the only way you could get sound out of your computer. And what we're going to do today is really crazy, which is we're going to generate these things on the fly. They're all binary data and all, and play them using our web browsers. So what I have here is a simple, not very simple, but a chaotic diagram of what a wave file looks like. And I don't want to dwell on that, but what I want to emphasize is the fact that we're going to start off with this idea that we want to make sound using a computer. We're going to go all the way down to the samples themselves. We're going to generate that. We're going to turn it into binary data. And then we're just going to shove that into your web browser, and it's going to make sound come out, which is really awesome. So I don't know if everyone's familiar with data URIs. Is that something people have played with before? Data URIs are basically embedding binary data for a file type into a URI, which you can then give to your browser in something like an audio tag or an image tag, and your browser will attempt to display or play that media. So what we're going to do is we're going to create a data URI containing wave data and have our browser play that. But first of all, little binary conventions. Some of this isn't in the JavaScript core set, but I provide it because it makes the code really simple. To encode an integer into a character, we use this encode_int function, which basically gives you you pass it the number of bytes you want to encode that number into, and it gives you a byte with the code point of that character. And you're probably more familiar with the charCodette function in JavaScript. Basically what you can do with that is you give it an ASCII character, and it gives you the character code, which is actually the binary value of that character. So there's a little joke in here. The answer to life, the universe, and everything is 42. And actually, the creators of the ASCII code set were prescient enough to put that into the representation of letters in our computers, which I think is pretty cool. And finally, for data URIs, you have two choices. Basically, you can't just give your browser binary information. You can't represent that easily just as a string. So we use an encoding. And there's two encoding options for data URIs, base64 and escaping. And we're going to go with base64 because it's just a little bit simpler to work with. So when I have this B2A function, it basically converts an integer into a binary string into base64 format to make it easy to pass to the browser in a data URI. So before we go further, there's going to be a lot of code in here because this presentation is basically a code walkthrough. So if you'd like to follow along or you'd like to look back on it, the URL's here, and I'll put it up at the end of the slideshow as well. So let's get down to it and start encoding our own waves. So what I'd like to do is I'd like to present this as basically a pipeline system of different abstractions. So when we're talking about audio, there's a lot of different levels of abstraction that we can use. We can say I'm going to play the note A for 30 seconds. But when we want to translate that down to binary data, we need to jump down several layers lower in abstraction, down to how am I going to generate the samples for that note, and how I'm going to encode those into binary in the case of WAV files. So the first thing we're going to do, this is kind of just the boilerplate of this code, is some simple JavaScript that will munch together some strings, it'll encode some data, and it'll create a riff header, which is the basic sampling rate information, the basic bit depth information for a WAV file. So what you have here is you pass it in a sampling rate, you pass in a number of channels, basically a number of bits per sample, and then some data, which I'll get into. We'll do a lot of that very soon, and it'll generate a riff header that your browser will understand and interpret when you play the audio. So this is very, very low level, but we're still going to need to discuss some really low level stuff, some really low level building blocks to get to the point where we can just throw samples at our browser and have it play them. So one useful thing is a WAV file represents samples as binary numbers, and we have to encode them and pass them into the data stream. One thing that's a little bit simpler for you and I to think about is samples as a variation from from -1 to 1 as basically a floating point number. Because then we can plot like a sine curve, and we're very accustomed to a sine having the range of -1 to 1. So the first thing to do is build an abstraction where we can pass an array of samples, basically, in floating point form and convert those into bit values for the wave data. So this is just, I don't want to dwell on the code very much as to explain how each piece fits together. But basically what we have here is we're taking a floating point value and then we're scaling it within just the number range of our samples. So for example, if I have 16 bits, well, let's just go with 8-bit samples. If I have a byte per sample, I have 256 options for the amplitude of the sound at that time point. If I have a floating point number like 0.5, I might scale that to 128 for that specific value. So basically what we're doing here is we're iterating over an array of samples, and we're converting those into just integral numbers. One more detail here is that typically in audio for humans, we have 2 ears. So there's this concept of channels. So there's a left channel and there's a right channel, and we have different values at every time for each channel. So in this code, I'm just going to represent channels as another subarray. For each sample, you have an array with 2 values, one for the left and one for the right. If you've ever played with audio, this stuff is probably quite familiar to you. So what we've built so far is the top of this diagram, which is now we can just pass an array of samples into this code, and it will generate a wave file for you, which we can then use to play some audio. So let's now just throw some random data at it and see what happens. Let's make sure, well, for starters, that my OS X web browser works. But let's make sure that we're able to, just when throwing random data at it, hear that the browser is interpreting this wave file properly. So what I have here is a function called noise. And what it does is it basically generates a stereo sample for just a count number of times. So we just generate a random number for the left, random number for the right, and return an array of that. And what we do is we create an audio object, which is basically the JavaScript parallel to an audio tag. We pass it in what this wave function outputs, which is a data URI containing wave data. And then we just give it our samples here that we generated using the noise function. And this may be a little bit loud, so I'm going to turn down my volume. So cool. We're able to generate noise using JavaScript. I think that's really cool, because as I grew up with the web, dynamic audio was only something attainable through Java or Flash. So the fact that we can just throw some bits together, just mash it into a wave file and throw it at our browser and get sound out of that is really cool. But let's do something a little bit more musical. I think most of you are familiar with a sine wave, right? A sine wave is a very basic synthesis concept. It gives you this very round, familiar tone. And you can generate it just by plotting a sine curve over time. So in the next example, I'd like to give you kind of a convention. So when I was researching the current techniques for audio synthesis in JavaScript, I came across this very nice convention in a project called Jasmid, which is a JavaScript MIDI player, all natively in the browser. And the convention is to represent synths as basically infinite generators. So if I have a synthesizer and it's making a tone over time, I can just pop off a value for each sample again and again, infinitely even. And each value I can then add to my samples array and play that. But the point is, in JavaScript, you don't have, like in Python, like a generator that can go on infinitely. So we just create an object with a read function that we can use to generate values over and over again. So what we have here is just you pass in the sampling rate, which is necessary for calculating the period of the sine wave, and the frequency you'd like the sine wave to be. And we just iterate. For every sample that's read, we calculate the sine wave, the current point we are in the wave. And this object just keeps track of it as you go along. And then we call read repeatedly, generate an array of samples, and then we can play that, and we can have a sine wave come out. So the next step, once you can synthesize a sound, is to basically create that sample array. So what I have here is a convention, another convention. We're going to have a lot of conventions when we're dealing with this many levels of abstraction. But that convention is just called synthesize. And the idea is you pass it in a synth generator, you pass it in a duration, and then it will it will iterate. It'll call that generator over and over again, and it will give you the number of samples you've asked for. So what we can do now is we can create these generators for any arbitrary pitch, like A440 or A880. And then we can synthesize that, create an array of samples, and then we can use all of the machinery we've created already to put that into the browser and play it. So what we're going to do is synthesize A440 and A880. Cool. That was kind of short. There we go. So that's pretty cool. So now we have a sense of tonality, which is another level of abstraction over the raw bits that we're working with. And what we can do is we can start to build up songs with tones, like, you know, Mary Had a Little Lamb. We can start sequencing those into songs. But first, just a quick sidestep into attack and decay. When you have a synth, just the very most basic concept of like simulating a voice is that when you start a tone, it doesn't just start at the loudest it's ever going to be. It sort of fades in, and then that's the attack, and then it fades out, which is the decay. So it's very nice to just apply that little envelope to the sound, because it sounds a lot more natural than this chunky A440 we have. So this is what it sounds like with a kind of a slow attack and decay for A440. And for A880, this pluck is just a really fast attack and a slightly faster decay. Cool. So now let's start making songs out of this. In our note system, we have, I believe there are 7 distinct. Well, no, there's 7 white keys and there's 5 black keys, and those together make up the notes that we can produce using a piano, for instance. So what I've done is I've just encoded in the white keys here in an array, in an object called notes. And I've just added a little bit of code that will allow you to make a string of notes one after the other, and it will use a generator for each of those notes and then generate the number of samples for a duration you pass in, like, and then create the eventual full song that you want by just stitching together these individual generators one after another. So for instance, if you want to play a scale, which is just each note in order of pitch, this is what it sounds like. Cool. So what we've done here is we've put together sine waves. We've then applied attack and decay envelopes to them, and we've passed those into this function called music, which will just take the top level of abstraction, which is individual notes that we can communicate to as humans, turn those into sine waves, then turn those into bits, and then turn those into a wave file, which we can give to your browser. So there's a couple cool things we can do now that we can work at a level that humans like to talk about. One of them is just random patterns. So what's going on here is we start with a bass note, and then we just take a random step over and over again and generate another note. And that can produce some kind of cool generative music. But finally, the last demo I'd like to show you in terms of wave generation is a simple filter. So one of the most basic filters I ever played with as a kid was in the Windows, sound recorder. There was this echo filter, right? And you could record yourself making a silly noise, you could reverse it, and then you can make it echo, which was the most awesome thing you can do. And an echo is a really simple filter to code, actually, a very basic one, because you can represent it as a simple delay line. That is, the sound I make at one time, I need to repeat at another time, because it takes a while for my voice to hit this imaginary wall that it's echoing against and be reflected back to me. So basically what we do is we take sound at one point in time, and then we repeat it and add it to the sound ahead in time, basically just creating a delay. So as I'm making sound at time equals 0, for instance, I want to take the amplitude of that sound and overlay it further in time with a delay. So basically all you're doing here is you're adding together samples, because the sound, when we talk about it digitally, it's just a value for every given time. So what we do is we just shift forward in time and we add two arrays together. Like we have one array of samples and another array of samples. We delay the second one. We just add the numbers together, and we can produce a really cool echo sound. Pretty fun. Like this gets really exciting, and you can take this as a branching off point, and you can play with all sorts of different filters and synths. And there's the great thing about sound is there's a ton of literature. Like this is really, really old stuff. People have been doing it since the 50s. What's cool about this is now you can start playing with it in your browser, and now you can start sharing with people. Like the coolest thing I could do as a kid was, make something in, MSW logo that would make, play a couple notes, and then call my friend over and say, hey, look at this. But what I think is incredible about playing with sound in today's age on the internet is you can make something cool, you can put it on Reddit, or you can put it on your blog, and you can share that with people. And I think that's really profound. So a little discussion about this technique. It's pure JS. It's not without downsides, though, because you have to generate these samples ahead of time and then play them. And what I'd like to tell you about now is a couple new APIs that browser vendors are creating that allow you to play absolutely live samples with very low latency instead of generating the audio ahead of time and throwing a data URI at the browser. So Mozilla came out first with this, what they called the Audio API extension. And it was a very basic set of tools that allowed you to throw individual samples towards the browser, and the browser would play them with very low latency. And the other really cool thing it let you do was it let you play something like an audio file from the web, like an MP3, and then read those individual samples as they were playing in JavaScript. And you can use that to do things like create visualizers. You can do that to apply effects like the echo to the audio. Really, really cool stuff. And then a little while later, Google and Chrome came out with what they call the Web Audio API, which I think is, it's very early, but this API is really, really cool. And it has a lot of really diverse functionality, and it's based on what's a really useful means of working with audio, which is you have nodes that can be synthesizers or sources of audio, and you can connect those together and create chains of audio processing, because you're basically just applying a function or some sort of processing to samples at each point. But if you can represent those as nodes and do them really quickly with the browser, that's extremally powerful. And the Web Audio API has things like convolution filters, which can be used to create things like reverb. It has spatialization, so you can tell it, like, simulate that the audio is coming from this direction in space. Really, really cool stuff, and it's exciting to see that built into the browser and fast and native, so we can start experimenting with audio in a higher level. So, unfortunately, we currently are at a time where live audio is not very consistent between browsers. Mozilla has a set of extensions, Chrome has a set of extensions. They're not the same APIs, and on top of that, you can do things like this data URI stuff to generate audio. So really what you want is kind of the jQuery of web audio. So you can just give it samples and have them play those, depending on whether you have Chrome's APIs available or just fall back to data URIs. So one really good abstraction layer is Xaudio.js, and it gives you Flash, it gives you Chrome, it gives you Firefox, and finally data URIs. So if you actually want to go out there and make something that you can share with a lot of people, I'd suggest looking at something like Xaudio.js and trying to use that before jumping off the deep end into Chrome's APIs. So finally, last I'd like to show you some cool examples, get your creative juices going. First of all, I'd like to show you Jasmid, which is something I sourced a lot of the concepts for this talk from, which is MIDI synthesis in pure JavaScript. I think this is so cool, because MIDI is a simple way of representing instruments playing notes over time. And the fact that you can take that file format, parse it, turn it into JavaScript synths playing, turn those into data URIs, which is what Jasmid is doing, and then play those with the browser is just nuts. I think that's really, really cool. A recent cool experiment, and I think this is a great example of data URI, just plain old wave data URI-based dynamic audio working out really well, is this bit pattern audio generator. This was kind of popular on Reddit. I think it was on Hacker News. But the idea is some hackers figured out that you can just throw some bit patterns at your sound card and produce really interesting audio. So it only took a couple days before someone implemented in JavaScript using data URIs. So you can actually play with these live rather than writing some C code and compiling it and then sharing it with your friends. So this sounds really crunchy, but I think it's a really cool, fun way to experiment with numbers. It sounds like awesome chip tunes. And what's awesome about this is, never before have we been able to share things and experiment with things so quickly. Like this went from a YouTube video to a full JavaScript proof of concept in just a couple of days. What's going on here? So another cool demo is this this drum machine, which uses the Chrome APIs. So you can basically lay down different beats in a rhythm pattern and then play those. And it will take these instruments, it will pitch shift them to play the right pitch in these cases, and it will sequence them and play them. It's a really cool experience. And I think that it's very easy to get carried away with these sort of slides that make noise, right? It's really cool because I remember seeing Flash-based music production software, but really we're not that far away from playing with like drum machines and keyboards in the browser. And I think most of you probably saw this Chrome experiment called Lights, and it does a lot of cool stuff with WebGL, and it also has a lot of audio experimentation because the Lights video is driven by the data of your audio file. So really, really cool stuff, and I think there's a lot of potential to create inspired art this way. But the final example I'd like to leave you with is a full text-to-speech in the browser. This is just so thought-provoking because it's an old text-to-speech that was written in C that someone mistakenly converted to JavaScript. But what we have here is a web browser that can speak, and it doesn't just speak canned things. It speaks things you type in and reads them back to you. I think it's just incredible to think how far we've come.
From your web browser.
Right? Just as a JavaScript programmer, this is just, it's mind-blowing.
As with a lot of the audio data demos, you can take advantage of the...
So yeah, I think that there's a whole lot of potential for speech synthesis and other just amazing things we can do with the auditory sense that just haven't been explored yet in the world of native JS. Thank you, everybody. And
anyone have any questions or anything? Perfect time to ask. Questions? Must have some questions.
ideas, gripes?
Cool.
Yes.
Where is audio space in terms of live streaming? So where is audio API in terms of live streaming?
I believe Scott's actually going to touch on that, but my understanding is you create an audio tag that points you to a remote audio file, and then you can download that and play as you download, and you can even get samples off it in recent incarnations of the API. Yeah.
Are there any hints at 3D audio?
What's that?
Are there any hints at 3D audio?
Yeah, I think that the web audio API, it has what it calls spatialization, and I think what that allows you to do is simulate three-dimensional positioning of audio sources. Was that or were you thinking of 5.1 sound? Yeah, totally. I think one of the cool things is in this spec proposal they actually have they show you Quake 2 in the browser, and they say, hey, we can actually do spatial audio now natively using these APIs today. I think that's just mind-blowing.
When you were looking at the sampling rates in order to get the sound, did you find that you were able to use wider sampling rates and then be able to produce it more quickly? Or did you play around with that at all?
Yeah, I mean the sampling rate really determines how many numbers you have to generate to play any amount of sound. And JavaScript performance has gotten a lot better over the past couple of years. So I think my example is, I don't recall the exact sampling rate I was using, but you can lower that and you can get something that sounds really like a Game Boy game or a chip tune. But you can actually, I think you can get a decent sample. So right now I think I'm using 8,000 samples per second. It produces an okay fidelity, but really, for audio CDs we're talking about.
Sample where the music is more complex
Yes. It's something that was figured out a really long time ago. Basically, all the interaction theory, there's this theory in physics and math that to represent a pitch of a certain frequency, based off of human hearing ranges, you're able to calculate a basic, decent sampling rate for most people that's going to represent the sound of their full hearing range perception. So for CDs get pretty close, but you'll find people who are crazy or very, very enthusiastic will like to pump it up to something. And that usually only comes handy when you're doing things like mixing audio, because of some of the math and some of the loss of accuracy.
In your slides, you were able to set your sampling rate, but if you're using one of these APIs, are they doing that for you, and do they have any access to modifying?
That's a really excellent question. With the Mozilla audio extensions, basically what you do is you say, I want this sampling rate, and I'm going to just start giving you samples at that rate, and I'd like you to play them at this rate. And I bet there's something comparable for the web audio API. Yeah.
Well, I guess so. Oh, did you have a? Oh, go ahead. No, here.
I noticed in the data URI example that you didn't specify base 64 in the encoding. So you say audio / wave, and then comma, and then riff, and then the data. So what I've typically seen is in a data URI, you can specify the encoding type. I think base 64 is the assumed default, but is it better to always specify the type of data that you're working with, specifically because you are doing a lot of either base 64 or escaped, like hex, like /00, whatever kind of stuff. Does that work? Have you found that without base 64 it works everywhere?
I don't recall the data URI spec. I think it actually defaults to escape form, and you have to specify base 64 to get base 64. There's no comparable difference for code examples, but base 64 does have the overhead. I think it's like it can only encode 1 byte, 3/4 of a byte per byte.
And it's basically less efficient. So base 64 will blow out your data by 3 times or something like that on average, right? Yeah.
It doesn't matter too much when you're talking about buffers and memory that you're just telling the browser. In terms of what's inefficient, it doesn't add up too much, but it's still slightly easier, I think, to just deal with base 64 because it's really easy to manipulate.
Yeah, we use it all the time at Flickr. I mean, on inlining, CSS or little inline images where we can. I mean, it's great.
Yeah, totally.
Just curious.
So you mentioned that you can actually access the audio data of the MP3 file or whatever. So it's theoretically possible to pack, for example, a JavaScript file into a zip and then into MP3 file and using certain encoding, then download the MP3 file, then parse it into a JavaScript and execute it in the browser. So it's kind of okay. That's a hack, but just an idea.
Yeah, I think people have actually done things with live MP3 decoding and encoding in JavaScript. Thankfully, our browser vendors can give us just the samples using an extension of the audio API. But one of the coolest things I saw was a JS1K demo, which I think will fall back to JS1K demos are 1,000 byte JavaScript programs that can do really cool things. And what was really surprising about this demo is it was using data URIs, but it was generating MP3 data URIs to create, I think, Morse code sound. It was just mind-blowing. Yeah.
Cool. We're good.
Yeah, one more. What's the state of mobile devices like iOS?
Honestly,
Yeah, the state of mobile, like iOS.
the state of mobile and I presume Android and iOS audio. Honestly, I'm actually not sure. I think some data URIs are supported in later versions of WebKit, but other than that, I'm not sure what extent they have things like full-fledged audio APIs or extensions.
So I've had ones like WebKit 500 plus or something. I don't know where it's at, but
Yeah.
it's pretty low. So you could just look up whatever the WebKit build or whatever was supported, and then check what's on iPad 1 or something.
Well, I'm not sure. The annoying thing about web on mobile is that they sometimes disable features for performance. Yeah. Yeah. Honestly, the answer is I'm not entirely sure. It would be really cool. You could just open this web page in an iPad 2, for instance, see if it works.
Okay, we'll do that.
Yeah.
We'll let you know.
Thank you. Yeah, looping is. I think Scott's going to really get into this. Actually, I think I'll let Scott talk about this in this upcoming talk. Exactly. I was going to say Nyquist, but I didn't want to say the wrong theory, since Nyquist has done a lot. Yeah. Thank you.
Cool. Cool. Thank you.